just saying a few words and then so welcome everyone. It looks like a packed room today. Partly because there is a meeting here of collaboration on simulating the accretion flows of gas around black holes. It's called TCAP, a grant that was awarded and involves people within here, but also from other universities that are spending the today and tomorrow discussing the astrophysics of black hole accretion and how to simulate it best. Also, I wanted to mention that the deadline for registering to the conference that will take place, the Event Horizon Telescope collaboration meeting, the deadline for that is the 1st of November. So if anyone is interested, please go to the EHT collaboration meeting website. You can just Google it and sign up for that meeting. It will take place in Alway, not far from here, about 15 minutes drive. And it will deal mainly with how to image the shadow of a black hole. And Shep Boltmann, that is sitting back there behind the glass, is the director of the Event Horizon Telescope, and any question related to that will be addressed to him. As everyone knows, we have also the new administrator of the BHI that I introduced last week. He's now sitting in his office, Bill Naring, and happy to help with any issues related to the administration of the BHI. So without further ado, we will start with the introduction of the speaker today. Andy, would you like?
Great. So today we're going to have Subir Sachdev from physics tell us about exciting new developments in SY-K models and black holes. Go ahead.
Okay, thanks, Andy. So, as you all know, I presume I'm a condensed matter theorist and normally don't talk about black holes, especially to an audience of black holes, to experts. So I'm trying to keep the condensed matter to a minimum, although maybe not. But I'll try to present the condensed matter from a point of view that you'll see why we think there's a common. There's a quite a great degree of similarity, some of the issues that arise when you think about quantum fluctuations of black holes. So this is work that I'll talk about in collaboration with my student Wenbo Fu, that's a lot about using that, and also Richard Davison, who is a postdoc here at Harvard, and Yi-Fei Wu, who is actually coincidentally visiting Harvard right now. All right, so just some very basic condensed matter. So if you've taken a graduate course in many-body theory, what you learned is summarized in this slide. That is, we know how to solve free electrons, but it turns out that for most materials, the free electron starting point is excellent, meaning that you understand the free electron problem, you turn up the interactions, and you get a state that's basically free electron-like. In particular, in the free electron model, you would fill up some low energy states up to some Fermi energy. And then when you look at excitations, you create particles and holes above and below the Fermi surface. And to summarize a very long story, in the end, these particles and holes behave like they're almost free. So there is, even for a strongly interacting system, an effective description in terms of almost free quasiparticles, as we call them. And then we can write down equations for these quasiparticles, which are similar to the equations for weakly interacting particles. And that's, of course, the Boltzmann theory, which is the starting point for a lot of dynamics and special mechanics. All right, so this is not what I want to talk about. This is just to introduce what a quasiparticle is. There's another very broad set of studies in condensed matter, so you could say topological quantum matter. And the most interesting example of that is probably the fractional quantum Hall effect. And here all I want to say is that the fractional quantum Hall effect, of course, is very far from a free particle system. Here there's what we call many particle entanglement in the ground state. But nevertheless, the idea of a quasiparticle still survives. There are some new emergent quasiparticles here, which have fractional charge and fractional statistics and all kinds of exotic properties. But in the end, you can just think of them as little points that are moving almost independently of each other. And that allows you to predict many, many experiments. So what I want to talk about are quantum states, which we understand much less, where the whole idea of a quasiparticle doesn't work. That is, there's no way to think about the low energy excitations in some particle-like basis. And by a particle here, you should think of excitations which are in some loose sense additive. That is, if I give you one excitation, there could be another one. There's another excitation with roughly the sum of them. So that's a very general definition of what you might call a quasiparticle. And as far as we can tell from experiments and theoretical studies, there's a class of compounds that people like to call strange metals, and they are found in these high temperature superconductors. I'll show you one slide just so you can at least get a sense of they're real. But this is what we want to understand. We want to understand quantum matter where there is no particle-like description of the low energy excitation. Okay, so this raises a kind of a fundamental question. So if I give you a piece of some theory and say this has no quasiparticles, because I tested this particular quasiparticle and it didn't work, you can say, well, how do you know that there isn't some other complicated basis transformation, some duality, which will give you some quasiparticles? And that's really not, it's almost impossible for me to rule that out because I can't solve the theory exactly. So this definition I'm giving you of quantum matter without quasiparticles is a bit unsatisfactory because it's defining something by saying what it's not. I need a more positive definition which at least in principle will allow you to say, aha, this is some genuinely new state of matter. So one way, very useful way it turns out to think about this is to take a kind of a dynamic point of view. So in particular, you take your system and you kick it a little bit and then you ask, how long does it locally take to come back to thermal equilibrium? Now, if you have a quasi-particle system, the bottom line is this time is generally quite long. So when you kick it a little bit, you create some particles. Those particles have to find each other and collide with each other. And then after a few collisions, the whole system will locally equilibrate. So in the simplest models in simple metals like copper or silver, where you try to estimate what we call Fermi liquids, try to estimate this time, then at low temperature, the temperature goes to 0, the time diverges as 1 over temperature squared. Okay, so we think of that as a relatively long time as temperature goes to 0. In some other system, like the pressure quantum Hall effect, this time would be even exponentially large. So then, one way to define a system without quasiparticle is you can say, well, that's a system in which it equilibrates as fast as possible, very, very quickly. So then that raises the question, is there some limit? How fast can you equilibrate any system? You give me any system you want, which is, let's say, infinite system, which is at thermal equilibrium, I perturb it a little bit, and ask how fast can it return to equilibrium? And so, I studied lots of systems here in the old days, and I conjectured that there was such a bound that you could never equilibrate any system faster than this time, which is Planck's constant divided by the absolute temperature. Yes?
In astrophysics, we always talk about light crossing time being the fastest time scale of a system.
Okay, so first of all,
we are talking
I want to talk about a purely local. There's no space here. Right. I want to look at a given point in space-time. So I want to.
So it's not a macroscopic system.
I mean, if I take it's a macroscopic system, but I'm looking at local. I'm talking about local equilibrium. Right. Certainly, it can take a long time. If you heat up the system here, it can take some time for energy to diffuse or travel ballistically. That can be long, depending on the size of the system. We're talking local.
Isn't it that in certain degrees, the energy times the time is bigger than h bar?
Sure. I mean, dimensionally it comes from that, but I think this is still a fairly strong statement because it tells you, for example, there's no system, and there's other energy scales around. There could be coupling constants and so on. So, and for example, that's what happened in the Fermi liquid. It doesn't obey the dimensional analysis. There's some Fermi energy that comes in to make this work dimensional. So, I mean, okay. Anyway, so this was the claim, and I think it's turning out to be quite a significant lower bound. Okay. So, for example, if someone found a system that discloses 1 over square root of temperature, that would violate this. There's no dimensional reason why that can't happen. but it doesn't happen. And there's some fairly, I think, deep reason why it doesn't happen. We don't fully understand it, but anyway, that's where holography is helping us. Okay, so this whole set of ideas was actually put up, made much more precise by Mardasena, Schenker, and Stanford, who were motivated by gravitational analogies. But for a conventional condensed matter system, we define something, and I won't go into the details, something we call the Lyapunov time, which you can think of rather than the thermalization, which is the way I was thinking about it. It's the time it takes for the system to lose memory of its initial state. That is, if you look at a system, you perturb a chaotic system, and you look at it the Lyapunov time later, by that time it's very hard for you to tell what the initial state was. It's just lost memory of all the initial conditions of this chaotic. And so they're proved under certain physical conditions that there is indeed a lower bound like this. So things can't go chaotic as fast as you want by just turning up some energy coupling. I mean, a classical system, you can always turn up some rate in your Hamiltonian and make chaos as fast as you want. But if you can't do that, and there's a occasionally a thermal equilibrium, there's the shortest possible time to chaos. All right, so that's kind of the condensed matter introduction. What we want to study are systems that become chaotic as fast as possible. This is the way I'm saying it now, but in the old days I would say, well, that's quantum matter without quasiparticles. Okay.
So in other words, they showed that your C is 1 over 2 pi, is that what you're saying?
So
I'm trying to remember what
right. So of course the 1 over 2 pi depends precisely on their precise definition of tau. So depending on exactly how you define tau phi, the C will be different. So for my particular definition, there is no proof, and there is no estimate of what this is. But in fact, the whole game here was they came up with a very clever definition of how to define tau. And that clever definition also allows you to fix. And that definition was entirely motivated from gravity. But in the end, the final proof makes no reference to gravity. Okay, in black holes, what happens near the horizon of a black hole? They were converting these, you have a black hole and a white hole, and there's some cross-correlation functions, and you convert them holographically. It turned out to be this Lyapunov correlator, which is considered in condensed matter a long time ago. So it's all very beautiful stuff, but I don't fully understand them. All these Penrose diagrams and all these different things, but that's where it came from. All right, so now let me show you a plot that you all, oh no, sorry, I'm not there yet. So very quickly, some experimental data, just to make this real. So here's a high temperature superconductor as a function of density and temperature. And there's this regime here where the resistance is a linear function of temperature, the red regime, where we believe you're somewhere near this maximum chaos. And here's some data from transport. There's a lot of questions on how you interpret this data, but since there's nobody, the condensed matter people are over there, so you can't question me, just take my word for it. This is evidence. This is evidence that all these systems are very close to this chaos bound. All right, so now things you know very well.
the axis of
I have 30 minutes. So. Okay, you know the axis on this plot. So this is the famous LIGO plot. And here I want to think about, not all this stuff. This very last stage, the ring down stage, where you have a black hole equilibrating. So that ring down time you can compute from Einstein gravity, and that. For this black hole, okay, I probably...
It's the light crossing time.
Yeah, it happens. That's true. It's 7 milliseconds. So it's just, nothing's been seen there, but maybe someday they'll see that. But also, and this is the ring down of a classical theory where the black hole is completely featureless. However, there's Hawking taught us the black hole is not completely featureless. It's got lots of degrees of freedom. It's a thermal equilibrium, has a huge entropy, which is the Bekenstein-Hawking entropy, and a temperature, which is the Hawking temperature. So this depends on h bar. But a curious relationship, which is the key to what I'm discussing really, is this relationship between the ring down time and the Hawking temperature. They're related in exactly the same way as is Lyapunov time for systems without quasiparticles. It's exactly this relation that this purely classical time is related to this quantum temperature. Of course, so if you think of it classically, well, it just comes from Einstein's equation. But if you think of a black hole as a quantum system, then this time is the time to quantum chaos. It's very much a quantum mechanical thing. But there's this strange connection between the classical and quantum, which is, of course, at the heart of holography. And of course, in this case, if you put in the Hawking temperature, the H bar cancels out, and you get a thing that only depends on G and C and M and things like that. All right. Okay. So that's the kind of superficial connection between, if you wish, but I think it's a very deep connection, between quantum matter without quasiparticles and black holes. They share this time to chaos, which is H bar over temperature. Okay. All right, so now I can talk about the SYK model. So this is a very specific model, which is both a strange matter without quasiparticles. You can show that from the condensed matter side. And it also looks like a theory of gravity. We don't fully understand the theory, but we know something about its low energy structure, quantum theory. And it looks exactly like a class of theories on anti-de Sitter space in 1 + 1 dimension. So here's one example where we can show that this is not a coincidence. And there are others that have been conjectured before, which I won't discuss, but this is the one example where the most progress has been made in making this connection as firm as possible. Okay, so that's where we are. So this model that I'll talk about, as this picture indicates, is a model that has no space. Everything is connected to everything. So it looks like a model which is in 0 space in 1 time dimension. Or you can think of it as something that's living in space, which is this board. But you look at a very low temperature, so that really the light crossing time is very short. You're looking at much longer time. So everything is talking to everything else. Okay. So either it's a small system in finite dimension or a 0-dimensional system. And the theory of gravity will have time, and this is space here, but also have an emergent direction. That's the holographic direction, and that's the second dimension in ADS2.
So
yes.
You can talk about the quantum state, but
yeah.
How do we know that that's the strange metal type quantum state? Is the argument that you've given that because the entropy is large?
Well, I'm going to solve this model. I haven't even defined the model. I'm going to solve the model, and I'm going to show exactly these two things. I'm going to show this explicitly. That's the next 15 minutes. That's what I'm going to show. Exactly what you asked. What I won't show, which is just for the lack of time, and it's also not my own work, was that this lower bound, this Lyapunov lower bound that was proved by Marta Senashenko in Stanford, is exactly saturated by both of these things. That's another reason why this SYK model and the theory of gravity. The second one was known before, but this was established relatively recently. Okay, so here's the model, and it's really completely defined by these 3 lines. You can give these 3 lines to the CMSA, and they should go and work on it. It fully defines the problem. You have some like fermion operators in anti-commute. These are the usual fermion anti-commutation relation. And the Hamiltonian is just some generic 4-body term of the fermions. Now I've defined it in a way that there's also a conserved quantity with supported in charge that computes with the Hamiltonian. We don't need that. But for the strange metal application, that turns out to be important. So, but let's not worry about it for this talk. So the idea here is that you can take any 4 sites, and then there's some amplitude for fermions on site 5 and 13 to go to site 3 and 7, and so on. You pick any 4 sites, and there's some amplitude JIJKL for 2 fermions to move from 2 of them to the other ones. And then the basic property is that these are all independent random numbers with some non-zero mean and 0 mean. Okay. That's it. All right. So it's as simple a model that you can define with interactions, and they're just completely random numbers. Now you might, this is a model we worked on in '93, and I worked on it off and on over the past 2 decades in various aspects of it, which I'll summarize in a few minutes. And string theorists were very reluctant to get interested. Mysterious to me, but anyway, but partly because randomness is a very unfamiliar thing. But now, okay, I'll say the randomness here is kind of a tool that makes actually the problem simpler to solve. That's one reason we introduced it. And second, in this case, the randomness turns out not to be that important. It's self-averaging. In other words, for most correlation functions, if you look at any property on site 5 or site 15 or site 11, it's the same. In the limit, you just need one sample, you take n goes to infinity, you just solve that already. So the randomness is there it actually is the key to allowing you to solve it exactly, but it doesn't really make the system that random when you observe it. Okay, so that's the trick.
Is the novelty here the randomness of the J, or the fact that you're requiring pairs of formulas? Like you're asking.
Well, I would say the pairs they're both important. They're both crucial features. Suppose you had only one. Suppose you had a single formula that could hop from 9 to 13. So that's what's called a random matrix model. That's solvable. It's not a. It has quasiparticles. It has very different.
That would have quasiparticles.
Yes. So it's very important that you forbid single particle hopping. You can put in pairs and triplets and quadruplets and won't change anything I'm going to say. But you have to forbid the single.
So the novelty is the pair,
yes.
And then you're picking a particular J for those pair interactions.
They are random. I mean, if you put some regular J's.
Particular J as in, like you're not picking anything.
Right. Okay, any other question? That is the full definition. Everybody know what the model is. That's the model. There's nothing, you don't need to read string theory or anything. This is it. It's defined by these 3 equations. Okay, so now this in the limit of large n, this can be solved. Well, that's an easy statement to make. We solved already many things in '93, and we're still discovering new things now about the properties of this model in the large n limit. And it has an amazing amount of structure, including an analog of the Bekenstein-Hawking entropy. Okay, so if you just do a Feynman graph expansion and you average over J, graph by graph, you get these very simple looking equations. For the Green's function in terms of this is just Dyson's equation, and the self-energy is the cube of a Green's function. So that looks, deceptively simple. Surely you can solve that, but these can't be solved exactly. We can only solve them in various asymptotic regimes. And again, there's a huge amount of structure in the solution of these equations. It's some kind of nonlinear integral differential equations. All right. So this, follows after a few lines from here. If I had a blackboard in 20 more minutes, I would write them, but I'm not going to. Okay, so then now you can, as I said, you can't solve them in general, but you can try to solve them at low frequencies and 0 temperature. And the solution you find is of this form. That first of all, the 0 frequency component of the self-energy exactly cancels this chemical potential. And then the leading behavior is square root of omega in the self-energy, and the Green's function is also 1 over square root of omega. And you can determine the constant A, and so on, and this is true for any value of the density Q. All right, so this solution is already an indication that you don't have quasiparticles, because the Green's function diverges at 0 frequency. So the branch cut at 0 rather than any pole. And there are many other indications, but this was a pretty strong indication that there's no quasiparticles. Okay, so now, all right. Now I'll list various properties that were discovered over the years and how they started looking more and more like a black hole, and eventually give you, what is a fairly complete discussion of why this is somehow, these equations can ultimately, at least some aspect of them can be derived from Einstein's equation. I'll kind of show you how that works. All right, so this is something I've already showed you. Just for completeness, I show you the case that not just at Q equals 1/2, but for general Q, E is something that measures the particle hole asymmetry. That's telling you whether it's easier to add a particle or remove a particle. That just depends on the density of the system. Then a key step was this observation by George and Parcolet that you could actually solve these equations I showed you earlier. This is just coming from this equation at finite temperature. And the solution looks like this at low temperatures and long times. And this form may be suggested to some of you in the audience. It's the kind of correlators you get in conformal field theories. But it just emerged. It seemed quite magical the way it is observed. But that turns out to be the key, one of the key observations. There's some kind of very large symmetry here in these equations. And then with my friends Antoine and Olivier, we computed what I'm calling the GPS entropy, which we found that if you took the system and just computed the free energy, and then the entropy and took the zero temperature limit, that you had a finite non-zero entropy. Okay. All right, so this is where things stood way back in 2001. And then after that, nobody really worked on this, but there were a different set of developments where people started thinking about black holes as dual models of strange metals, the ADS-CFT and all of that. And in particular, there were a set of models that were solved by the group at MIT. I should really have their names here, I'm sorry. Hong Liu and Jen McGreevy and David Vague and Tom Faulkner, who looked at what happens to fermions moving near the horizon of an ADS-2 black hole. And from their solution, I observed that all of these properties that were just determined for this model seem to match perfectly. If you look at a fermion moving in the background of a black hole, it would have exactly this correlation. There's a black hole as an entropy, and how that entropy depends on charge, I showed more recently, also completely tracks what you get from Einstein's equations. Okay. So this is kind of the picture that you have in mind, and I'm going to, yes?
Worth mentioning to this audience that it's also true for the extreme curve black holes.
Which one? This equation?
That you have this kind of ring function. And that's something that people in this room have been observing.
I see. Is that right? Okay, with this asymmetry from the form there, with this thing which is not the same for positive and negative frequencies.
Well,
yeah.
Yeah, but so far you described mathematical similarities. Is there some underlying physics?
Right. I'm coming to it. Yeah. Okay. 5 more minutes. So this is the picture that I kind of proposed in 2010. The idea is this SYK model, and you take put it on a finite space, that's the torus, and make the radius of the torus very small. Now, if this was this was the boundary of some gravity theory, that from holography, you know that if you took the boundary of some holographic theory with some density of particles cubed, you get, by solving Einstein's Maxwell equation, an anti-de Sitter space, which at low energies way out here has a black hole horizon with a finite entropy at zero temperature and an electric field. And what I just said in the previous transparency, that if you look at all kinds of properties here in gravity, they seem to match perfectly with all the properties we studied here. Okay. So now let me try to give a deeper understanding. So this seems like circumstantial evidence. I have two systems and everything matches, even quantitatively, factors of 2 pi, everything matches. So it was fairly convincing to me, but it didn't get everybody working on this. Okay, so now let me go back to these equations and notice one very important several important properties of these equations. So remember I said that this mu over here and the mu over there cancels, and this sigma goes as square root of omega. So at small omega, this term is much larger than that. So both of these terms and this term really don't matter at the low energy limit. So let me throw them out. Okay. Now look at these equations where you have G times sigma equals 1 and sigma equals G cubed. It turns out these equations have a huge symmetry. And they have a symmetry of diffeomorphisms or reparameterizations and gauge transformations. So you can check, and this is really again a few lines. If I reparameterize time to be some other time sigma, and then I reparameterize the Green's function in the new time after some scaling factors corresponding to the change in metric and the gauge transformations G. Do the same for sigma. The equations for capital sigma of sigma 1, sigma 2, and G will be the same as these equations expressed in terms of tau 1 and tau. So the whole theory, at least the equations you get at low energy, have this huge symmetry, reparameterizations and gauge transformations. On the other hand, the actual solution I gave you, this is this property of these equations. So the actual solution is here. This solution is not invariant over these reparameterizations. So that solution was tau 1 minus tau 2 square root. Now if you do this transformation on that function, you find it's not invariant. But it's invariant under the subgroup for the diffeomorphism, and that subgroup is SL2R, which is the informal group, 0 plus 1 dimensions, I guess. So it's all kinds of transformations like this. All right, so that's the rough idea then, that you have, at least at low energies, you have this emergent diffeomorphism and gauge symmetries. But in the actual vacuum that you choose, the vacuum solution has it broken, but it's kind of spontaneously broken down to SL2R and global U1. I didn't show that. Okay, and now the point is that this is exactly what these are the symmetries that point to gravity, because reparameterization gauge invariance are exactly the symmetries of Einstein-Maxwell theory, and also SL2R is the isometry of ADS2, so that's why ADS2 appears. So, we know that Einstein gravity is reparameterization invariant, but our vacuum, the Minkowski vacuum, is not reparameterization invariant. It's invariant in the Poincare group. And so this is the analog of that. The vacuum is invariant in SL2R, the theory is reparameterization invariance, and so the effective theory is a nonlinear sigma model on if S1 slash SL2R, and that is basically gravity on ADS2. So that's the reason. Okay.
That's not physics, that's still mathematics.
Okay. Well, okay, I gave you both the physics and the mathematics. You take your pick. I give you all the physical properties, they match. This is the mathematical justification. So you can take this further. Now, I guess I'm out of time. So there's a lot of work here. So you can now look at reparameterization that are almost SL2R. So you look at what is the effective action for reparameterization that are almost SL2R, and then you get an effective theory, which, okay, I don't have time. It's some complicated term. This was obtained by Marlesina and Stanford, and this is a new thing that we haven't published yet, having to do with the gauge symmetry, which relates to the charge transport properties. This thing is the Schwartzian, and all the coupling constants can be determined. And so this describes the long time fluctuations of charge and energy fluctuations in this SYK model. So this can be derived with some numerics and analytic calculations from this specific Hamiltonian. All the steps can be done, and in principle all the coefficients are known numerically for that particular Hamiltonian. Okay, and then the magic is that people have started from gravity theories on ADS2. That was done in this paper by Marlesina, Stanford, and Yang, and Jensen, and Engelshoy, and Verlinde. They get the same effective action, at least this term, starting from gravity. So you take gravity on ADS2, in other words, you take the low energy limit of this guy, or you take gravity in ADS2, you integrate out the bulk, and you get some effective theory on the boundary. And these two approaches give you exactly the same theory, which is this theory. I should say that we haven't fully established this yet. At least for this part, that's been established. Okay, so that's basically what I want to say. Now you can compute various things. Me being a condensed matter physicist, I want to compute things like diffusion constants and conductivities, and you can do that in some extended higher dimensional models. And again, it agrees. It's no surprise given all these correspondences that I just described. There's one relation that I should point out for Andy's benefit, which I think, which is right here. You can think this gamma here is sort of like a central charge, which determines the specific heat. But when you take the charge case, there's an electric field that you need to induce, and you get a shift in the central charge, it goes to the square of the electric field. And that's similar to models that Hartmann and Stroman demonstrated. Many other features are different, but that feature seems to be common. All right. I guess that's all I want to say. Forget all this. So there's my summary. So there is at least one specific Hamiltonian, a very simple Hamiltonian, which is both a strange metal and a black hole. And one of its characteristics is that both of these models, of course, have this fastest possible thermalization or chaos time. Thanks.
So, I think I missed it just there at the end.
Okay, well, it was very fast,
But
yes.
to call it a strange metal, I sort of expect there to be interestingly large spatial dimensions so
Yeah.
that I can talk about
Sure.
diffusion or conduction or
Yeah,
whatnot.
so that's the
But we
model.
got this out of just...
Right, so there's this
common
extended
sense.
model, thank you for that question. There's this extended model actually proposed by Ying-Tae Gu and collaborators, where you take this SYK dot and you pick a whole bunch of them and you couple them in some spatial lattice. And for this model, you can then talk about number diffusion energy. So it turns out what they showed is that the ground state of this kind of model has energy diffusion, and the extension we worked on it also had charge diffusion. So that's already quite non-trivial. I mean, there's very few models where
So
you can
this
show
is just
this.
like putting structure into your
Right.
four-point couplings.
That's right, that's right. There's some spatial structure you put in. And you get a model, but you can, in the larger limit, you can prove it has diffusion, which already is rather amazing. But even what makes this a first is that it's really the first model that has diffusion but does not have quasiparticles at zero temperature. So that you can now look at various correlation functions and I mean, we know that also saturates this bound on tails. And the part that I skipped is that if you take these diffusion constants that you get from a model like this, they actually match very well to these theories where you have an infinite spatial dimension, but you put in these axion fields to dissipate momentum, and the properties on this kind of gravity theory quantitatively match in many respects what you get from that coupled SYK. So that's this. These are two direct. You can put spatial structure in both directions, and again, they tend to agree. They do agree for these class of models.
If they connect to black holes, are there predictions of these models for experiments on strange metal?
Well, I mean, so these are, the one prediction is obviously in the lab. It's got a finite ground state entropy per site. And nobody really believes that's true in the actual strange metal. So it's a mean field model. It has some anomalous features. Another prediction that comes out, which I think also...
That can't be true in a strange metal.
It would be very surprising. I mean, most strange metal actually becomes superconducting. And then, of course, there's no entropy. It's hard to believe that a model that didn't have a large N limit with infinite couplings, which are so large everywhere, that somehow had a finite ground state entropy. Or zero temperature limit of a third law of thermodynamics is violated.
But at large, I mean, there could be energy spacings that are order 1 over n that become degenerate.
Well, they're about e to the minus n. So there's no degeneracy. That's why it's important to say that all of these models do not have any degeneracy, I mean, any significant degeneracy. But it's just that the energy level spacing is more close. So if you have a typical quantum system, if you look in the middle of its spectrum, the energy level spacing is e to the minus n. It has to be because there are e to the n states. But if you go to the bottom of the band, near the ground state, in most systems, right near the bottom of the band where you have quasiparticles, the energy level spacing is 1 over n or 1 over n squared or something like that. Here it's e to the minus n all the way to the ground state. So that's why the entropy, the zero temperature limit of the finite temperature entropy is not zeros. So it violates the third law. So, these are solvable models. They're teaching us a lot. The solvable models with quantum chaos and non-quasiparticles.
So is the GPS entropy, is that a correction to the Bekenstein model?
No, that is the Bekenstein model.
Yeah, so I'm confused. So I thought that was the attractive feature of this model.
Depends on whether you're working in black holes or it's the attractive. So if you're talking about a real black hole with a finite size, a charged black hole, this is perfectly fine. But if I'm going to fit the data on condensed matter, then that's not so attractive because they don't have that much entropy. They have less entropy. So there are other models which are much harder to solve. Fermi surfaces coupled to gauge fields, and there's a lot of work in that direction that we've been doing over the years, which has been inspired by these exact solutions. But they are different. We don't know what the gravitational duals are there. That's a much harder question. Yeah.
So I wanted to explore this light crossing time business.
Okay. Yes.
Right? So you showed that this h bar over kt,
Yeah.
if you plug in the Hawking temperature,
Yeah.
you get a time scale which is in fact the light crossing time of the
Yes.
black hole.
Right.
Black
Right.
hole as a size,
Yeah.
nothing can happen faster than the light crossing
That's
time.
right.
Right? So that works.
But things could be much longer.
It can take longer, but
Yeah.
it's a kind of a lower bound.
Right.
It's
But
fine.
the fact that it's parametrically the same as the lower bound is very significant.
Great.
That's telling us about chaos on black hole.
Sure.
It could have taken a much longer time.
No, but I want to now look at the right-hand side of that equation.
Yeah.
Because you started by looking at some condensed matter system
Right.
with a real temperature, right?
Right.
And you said, I've got now a lower bound on the time of something.
For this so far, this is the only system in condensed matter where we know where you saturate the bound.
So what I want to ask is, making this connection, is this saying that this entangled, strange metal stuff has got a characteristic length scale? That ultimately it is the correlation length of whatever is.
No, I mean,
How do you get a time?
from temperature and h bar. So the ground state is scaled, and the ground state is reparameterization. It has time reparameterization invariance. There's no natural time in the ground state. And that's these huge symmetries in the ground state. It's invariant under reparameterization, but when you put a tiny temperature, that breaks it just a little bit, and that's the only time that appears that determined by temperature. So that's kind of the heart of it.
But isn't there some spatial correlation length in
Well,
the system? It has to be, right? At zero temperature, presumably it is infinitely correlated.
Okay, C is infinity in condensed matter.
Is it? I mean, this is where I'm coming. Yeah, is the theory? You may say C is. It's finally it's field theory, right?
Okay, no, I'm
It
just
is
joking.
field
But
theory, and it's got C somewhere in it.
right, okay, no, all right. So the point is that, right, if I take a more realistic model, like here, so here I'm taking, say I take a realistic model of finite range interactions. So this model will have a characteristic velocity. So for the cases where I can really show, for example, or at least make some progress in showing that some finite dimensional model is due to gravity, then this model on the boundary typically is a conformal field theory. It has a velocity, and that velocity will become the velocity of light in the dual. But that velocity, is in real numbers is 100 times smaller than the velocity of light. It's determined by some scale that determines some exchange energy or something. So that depends on your lattice. There's one velocity. But other than that one velocity, you don't need to know anything, any other numbers about this theory.
But when you go to this bound, is that velocity going to C or?
So the bound, the
Where does
velocity
the bound-
doesn't appear in the bound.
Well, the velocity doesn't appear.
But there is something called the butterfly velocity, which I didn't talk about, which is how this chaos propagates in space. That's another very beautiful subject that a lot of people are working on. And that velocity will come into what's called the butterfly velocity.
Is there something that corresponds, on the condensed matter side, there's conductivity and the limit of superconductivity where the entropy disappears.
Yes.
Is there something that corresponds to that on the black hole
Sure.
side?
So there are, if you take some black hole solutions, you can get various Higgs fields condensing, and so this, in fact, it was by this condensation. So there's a theorem, folk theorem, and I shouldn't talk here, but correct me if I'm wrong, but there's something called no-hair theorem or something. Black holes can't have any features. But then I think Steve Gubser was probably the first to point out why this condensed matter inspiration, that at least in anti-de Sitter space, black holes can have lots of hairs, they can become superconducting. And those are duals of superconductors that you will get on the boundary.
Yeah, so I think we actually need to move on to get time to our next speaker, but yeah, let's thank our speaker again.
Yeah, it's fine, but go ahead.
Yes, our next speaker is Dimitrios Psaltis. Dimitrios is a professor at the University of Arizona, but for this year he's visiting as a Radcliffe Fellow. And Dimitrios is right at home in the BHI. He works on a number of things, including strong gravity, neutron stars, black holes, the Event Horizon Telescope, and so forth. But I think something he has a particular fondness for and also talent is identifying probes and tests of strong field general relativity, both extending from the theoretical side to match observations and thinking of clever ways of using observations. So he'll tell us a little about that.
Thank you, Michael, and thanks everybody for coming. I've had a wonderful time so far, let me say, all the PIs of the BHI being here, coming to this talks every Tuesday, so I'm very happy to be part of that whole experience in a different way. And we've already had a number of talks and some discussion here about issues related to fundamental properties of black holes when you think of them in the theoretical physics context, not the astrophysical context, related to black hole thermodynamics, related to the information paradox. We had a wonderful talk 2 weeks ago about potential resolutions to those problems. And I'm not going to say anything more about that other than to say that some of those resolutions involve horizon scale structures that are rapidly fluctuating around black holes. And when you tell an astrophysicist horizon scale structures, then you're suddenly bringing something that is quantum mechanical and microphysical into the realm that might be potentially observed. So what we did this past year with Steve Giddings at UCSB, and I believe many of you know Steve quite well here, we tried to understand, we tried to do a phenomenological model of what could those sorts of quantum-inspired or quantumly inspired horizon scale fluctuations, what kind of implications might have for observations and how we might want to say something about it.
These were not ruled out by LIGO?
No, and I can say something about that in a second. Yes, they're not. LIGO is, with all its wonderful things that it does, is an order 1 test of gravity. And it involves a very particular aspect of gravity that has to do with the dynamics of gravity. So this is superb and beautiful, but there's a lot of room to do things, even in the age of LIGO. We can spend more time talking about it. So the particular, actually Steve wrote a paper about LIGO in that concept, but the particular...
But wouldn't it be very hard to identify equations which
yes.
change things at the horizon? If the horizon scale that didn't mess up LIGO.
Okay, let me parenthesis. So the main thing that LIGO measures, especially at the ring down phase, is effectively what happens to the space-time at the photon radius and outside. It's effectively what we're doing with the Horizon Telescope. And you can do a lot of things inside, but most of the gravitational waves that you generate inside are actually going to be lensed around and not going to go further out. What we're doing here is we're introducing ad hoc perturbations. That's what Steve, for example, was doing. Ad hoc perturbations at horizon scales that die very quickly outside the photon radius, photon orbit radius. And those perturbations are not solutions of the Einstein equations, are introduced by some other process, and those do not propagate. So those things will not propagate as gravitational waves will never detect them. The question is how do those things, whatever leaks outside of the photon radius, couples to whatever in-down effect you have there, and how does that propagate to infinity? Yes, it might be quite difficult to come up with ways that leak outside the photon radius, but it's very easy to have things that die very quickly and never propagate, not affect anything to do with it. At the spin, at the situation where the two black holes are relatively far away and they're just slowly moving closer and closer in, then the effect can be practically zero, because those things don't propagate. I mean, again, this is the phenomenology that this goes on. Close parenthesis. The particular aspect that we were looking for is, and related to this particular audience, is the Event Horizon Telescope. As you know, this is a collection of pretty much every single millimeter telescope around the globe, from the South Pole to Arizona, from Hawaii to Chile, and 2 telescopes in the European Alps and the Pyrenees. And the main goal of the Event Horizon Telescope is to take the first ever pictures at about millimeter wavelengths of astrophysical black holes with horizon scale resolution. The wavelength of observation was picked such that the accretion flow of the galaxy in the atmosphere is transparent, so we can actually see all the way down to the horizon. And the question that we're trying to ask is, what if there are horizon scale fluctuations, what will they affect? And what I will focus on today is what we call the black hole shadow, which is the primary goal in gravitational physics of the Event Horizon Telescope. But before I tell you what the effect will be, I will need to motivate some of, and help you understand some of the issues by explaining what the black hole shadow is and how it works in non-perturbed general relativity, just care about space-times. This is something that it's an idea that goes back to Bardeen, the idea of the shadow, 1973, and Luminetti, 1979, who asked a very simple question. It was so simple, it was actually in a conference proceedings, not really in a referred paper. What if somebody shines light from behind the black hole, what would happen? And the answer is, of course, trivial, and I'm going to show a little animation here, not to be pedantic, but because this is a diagram that I'm going to keep on improving as we go, adding more and more effects. And the idea is that if you have from far infinity a wall of photons that are meant to be all photon trajectories, not trajectories, that go towards a black hole, the green is meant to be the horizon, and the dashed line is meant to be the radius of the photon orbit, the radius at which photons orbit. Then clearly, because of gravitational lensing, the trajectory is bent, and every trajectory that at some point or other crosses the photon orbit will end up into the horizon and will never appear from the other side. So the blue trajectories are meant to be the cross-section of all the photon trajectories that actually end up in the black hole. And if I were to take a picture from the other side, I will see nothing but a shadow. That's the definition of a shadow, right? Something that you put that blocks the photons that come from behind. So what we say is that the black hole shadow is nothing but the gravitationally lensed outline of the photon orbit around the black hole. So, of course, we don't expect anybody to be shining light behind astrophysical black holes. What we do expect is that we're going to have plasma around the black holes. The plasma is going to be very hot. The plasma is going to generate particular radiation. And the whole point of that TICAN collaboration that we're discussing today and tomorrow, as Adi pointed out, is to generate a lot of those models of what do we expect those black holes to look like. And this is a particular simulation by our group and Rames's group here, by Ian Deus primarily, who is sitting in the audience down there. And this is meant to be what you would see if the black hole in the center of the Milky Way was emitting the way that we think it does. There's a very hot plasma, there's particular flux strips that come in and out of the side, there's reconnection, there's heating, there's all sorts of things. And that red line out here outlines what you would call the black hole shadow as we described it before. You might say that this is, you can barely see anything, let alone the black hole shadow. Of course, I can play with the color code to make you see the black hole shadow more, to see the black hole shadow less. But just to see exactly what it looks, the best way to do it is plot everything without colors, take cross sections, and these are two particular cross sections, 45 degrees and 90 degrees in the brightness. And as you get closer and closer to the black hole, you get more and more hotter plasma, more and more emission, until you hit the location of the black hole shadow where you have a sharp gradient. Right? So the location of the black hole shadow, whichever way you look at it, this is the other side that you can barely see on this particular rendering, is the fact that we identify the black hole shadow as the place where we have these extremely steep gradients in the brightness of the image. This is something that is going to be relatively easy to identify and measure with the Event Horizon Telescope, assuming that everything works and nature is good with us. Now, of course, you're going to say the idea of a photon orbit might be something that you would expect for a spherically symmetric black hole, a Schwarzschild black hole, right? Because the metric is completely spherically symmetric, so whichever way you send a photon around at that particular radius, it will orbit. Well, it turns out that the Kerr metric of a spinning black hole, has some very interesting properties that allow you to have constant radius photon orbits, independent of the orientation of the orbit and independent of the spin of the black hole. Now, because this metric by itself has has a non-zero quadrupole moment, is not spherically symmetric, and because of frame dragging, those orbits are not going to be on a fixed plane. They're going to be moving pretty crazy. And the easiest way to do it, instead of waving my hands, which I like doing, is show you this little visualization done by Leo Stein, who's a graduate student at MIT, he's now at Caltech, who did that little, you can find it on the web, it's a little, Java or Flash, whatever it is, visualization where you can play with the spin of the black hole, you can play with the radius of the orbit, and you can see how the orbit looks like around the spinning black hole. This is a non-spinning black hole, so you have the nice photon radius there, and I can turn it around. And you see that's the nice circle. But if I come now, on this side, and spin the black hole up, because I'm going in the prograde direction, the orbit became bigger, but if I change the orientation of the orbit, then I get a nice spherical photon orbit, which is not on the same plane. And of course I can change, effectively you change the radius of the orbit, and by that you change the relative orientation of the angular momentum of the photon. So these are null geodesics, these are photons, these are not particles. The space-time is scared, in this particular case almost 0.7 of maximum. The space-time has a significant quadruple moment, so it's not spherically symmetric, and yet there is a way to have photons, there are radii, where the photons will be on a constant radius orbit. It's just that the orbital plane of the orbits evolves extremely rapidly because both of the quadruple and frame rapidly. This is a very interesting and, I guess, in the beginning, unexpected property. Usually when you have a oblate astrophysical system, you cannot have spherical orbits if you're close enough to feel the oblateness. I mean, this is just about the horizon.
Does spherical mean something other than just the
constant radius?
Well, but what is, that's all coordinate dependent.
Correct.
So this just means the geodesics take place on some fixed, what?
It depends on
one surface.
Exactly, that's exactly what it is. So you can set up a foliation of coordinates in your parameter space, so that particular radial coordinate is fixed, and that's what is defined as a spherical orbit. It is mathematically something that allows you to solve things because you're solving things on the surface, but of course the proper distance or quatorial distance and everything are very different. Absolutely right. But there's something that we can do that.
What characterizes that surface geometrically? How would we describe it geometrically? Is there an equation for that?
For this particular surface, it's effectively the null geodesics, unless you have a commensurate, evolution of the orbital plane and everything. The null geodesics will cover the entire.
Is there some local characterization that says when you're on that surface?
Is it constant extrinsic curvature?
No, it is not. I mean, again, this particular case, they're Bohr increased coordinates. They're constant Bohr increased coordinates in the Kerr space. But I mean, is that the characterization? So this is one interesting property of the space-time that becomes relevant. But if you want to do something that is coordinate independent, you can ask yourself, well, I go at infinity and I calculate the outline of the black hole shadow as I spin the black hole. What will it look like? And in the beginning, we all thought that we're going to start getting an oblate character because of the oblate character of the space-time. So what we did, and this is with my former student Tim Johansen, this is what the black hole shadow looks, the outline in gravitational units, a little over 5m in either direction for a non-spinning black hole. And this is what happens when you start spinning the black hole. And you can make it just stops at 0.4 in this particular case. It just moves to the right, to your left. So it depends on the orientation of the black hole speed. So effectively what happens is that the black hole, the quadruple moment of the space-time will try and compress the black hole shadow in order to give it an oblate shape. But photons that go this way go with the rotation of the orbit, of the spin of the black hole, so frame dragging goes with them. Photons that go that way go against frame dragging. And remember, what we see is the gravitationally lensed projection of the photon orbit, effectively, or whatever those photon spheres are. And frame dragging affects lensing in a way that effectively at the quadruple order cancels completely the oblateness that you would expect from the rotation of the black hole. The size of the black hole shadow remains more or less the same. It is almost a circular shape unless you go to almost maximally spinning, in which case the octable becomes important, like a cube. And the only thing that happens is that the center of the black hole shadow gets displaced from where the black hole is.
So how do you also get a flattening on the side?
Only at 1. You have to go to 0.9596 in order to see that flattening. The simulation that I showed you before has a 0.9 spin. Where do you want here? And this is almost a perfect circle.
So are we saying because it's very difficult to measure the spin and the shape?
Exactly.
So how would we measure the spin?
in order to measure the spin, you have to look about the plasma. To look at the plasma, look for location of the innermost stable
Well,
cycle.
there is another effect, which is
No, but the
orbits.
polarization.
No, there is
Polarization
the
is
Doppler
fine.
effect, the beaming effect would be different. As you increase the spin, the speed of the material
Correct.
is getting higher, so you get more beaming.
And if you get material that is in stable orbit, stays for a few more orbits inside what you would call an innermost stable circular orbit for a spinning black hole, then you would put a limit on the spin. I mean, there's more ways that you can do with the plasma, but you cannot live with the black hole shadow. So the black hole shadow is not a good measure. Knows very little about this.
But is there a polarization asymmetry in the shadow?
There will be,
If it's spinning, there's certainly, I mean,
if we can predict the polarization, because the only thing that you do is you see effectively the polarization from behind.
right.
You're talking about polarization of the photons, right? Like,
Polarization
you're
of
speaking
photons
theory,
shouldn't,
like,
shouldn't become polarization for
Correct.
Yeah.
So what you're saying is that you're seeing the gravitational-less polarization of things from behind. So unless, and I would like to do the calculation and see what exactly it is, it will depend on what the polarization structure of the accretion flow behind that you see the shadow against.
We had a paper on that with Avery Broderick about polarization.
Mhm.
But the biggest effect is the Doppler
effect.
beaming, which is larger when the spin is large.
So numerically, we can calculate what the relative asymmetry is, the size of the shadow in this direction versus the size of the shadow in this direction is. Of course, depends on the inclination. If you look down the pole, it should be 0, and causes sine inclination to the 3/2. There is this interesting combination, the spin and the quadruple of the black hole spacetime. This is when the octuple becomes important. And of course, the no-hair theorem tells us that the quadruple of the spacetime is equal to the minus spin square, which is why when the no-hair theorem is satisfied, if these are Kerr black holes, there is no asymmetry up to the quadruple order. So the only reason that I brought all of that is to say that in principle, we would have liked to use the shadow of the black hole to say something about the black holes themselves, spins and inclinations and orientations and everything else. It turns out that we won't say much about that because the black hole shadow cares nothing about that. But if it cares nothing about the properties of the black hole, then the only thing that it cares about is the space-time, right? This is a prediction of the Kerr space-time that works only for the Kerr space-time. And as you can see from here, you can calculate, just so it's slightly different, as a function of the inclination angle of the black hole and the spin of the black hole from 0 to 0.99, you can calculate the characteristic size of the black hole in gravitational units, 5, give or take 4%. This is where the octuple comes in. And this is a beautiful, 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 effectively no free parameter prediction of general relativity. Right? There's nothing that you can do to your space-time within general relativity to get away from this. Not only that, of course, this is gravitational units. What you care is how big is the mass of the black hole and how far away it is, because we're measuring angular units. And for that, even though we know neither of the two very well, we know the ratio, m over d, or the angular diameter of one gravitational unit at the center of the galaxy, because of the orbits of the stars. When you do the orbital dynamics of the stars, and we had that wonderful talk last Tuesday, I think it was, then you effectively do the same experiment further away from the black hole, and you measure angular sizes. So even though you don't know angular orbits, even though you don't know the mass or the distance very well, you measure the ratio extremely well. And when you do the two closest stars, SO2 and SO38, this is actually from this year, you know that one gravitational unit at the center of the galaxy is 5.09 plus or minus 0.17 microseconds. That's a 4% measurement. So we know what the black hole shadow size and shape is going to be at the center of the galaxy to within 4%, no questions asked, no parameters involved. This is a superb gravitational test that hopefully we'll be able to do with event horizon telescope. But if that is the case, and this is an example of what happens when you violate the no-hair theorem, when you start adding a quadruple moment that is not Kerr, and you start getting wavelengths in different sizes. But if the black hole shadow is such a wonderful probe of the gravitational field, what if we have horizon scale fluctuations of the gravitational field? Should we not be able to see them? So what we wanted to do with Steve, actually I was giving a colloquium at UCSB a few years back, and Steve said, what if we add phenomenologically a set of fluctuations of the space-time around the horizon that die rather quickly with a characteristic scale, say, of 1m? And this is the kind of thing that we added. relative amplitude of fluctuations that is effectively zero for a non-spinning black hole where the plasma is, but they have some significant amplitude where you might actually be able to see the horizon, the shadow. What if we put the characteristic wavelength of, say, of order m, because we don't know, this is pure phenomenology, just to see what the implication would be, and put some characteristic frequency that is 1 over m, and still love this 1 over 8 pi for reasons that I don't understand, maybe you guys do, but it doesn't really matter whether that 8 pi is there or not. And I thought this is a great project. We have the code. I go home, I'll press the button, and then it will pop out the result, and that'll be the end of it. Famous last words 2 years later. It turns out that this is not as simple a problem as you might think, if you thought it was a simple problem. And it turns out to be a little more complex problem in practically mathematical physics that has to do with geodesics and space-times, which I will describe in a second. To begin with, all the algorithms that we've had so far that do the calculation for static spacetimes made use of every symmetry in the problem that we could in order to make the calculation fast. So time independence and axial symmetry are two killing vectors that we are related to, involved two killing vectors that we use to make our calculations fast. That had to go away because here we'll have neither. However, when we threw in a random set of perturbations like we did before without thinking too much, this was the plot that I showed you before, the blue for a Schwarzschild spacetime, the blue trajectory sending the black hole, the red trajectories do not. We add a tiny perturbation at a few percent level, and that's what we got. So the trajectories came as soon as they hit the perturbation to be numerically non-zero. This is just really when the perturbation becomes important. They start moving to the wrong direction. And after spending too much...
This is physics or numerical error?
Numerical error.
It is physics. It is physics error.
Physics error.
Yes. it is. So it is neither. It is error, but it's physics. And it turns out that you have to be smarter when you do things like that. And the easiest way to think about it, we're using Eddington-Finkelstein coordinates, and when you start getting close to the black hole horizon, things, metric elements become zero, and they change sign. It's the whole thing that what you call distance outside becomes radius and vice versa. Like, you start introducing perturbations that you don't pay too much attention to, and suddenly your metric is going to have two time-like directions, or four space-like directions, or suddenly the phi direction becomes time-like. And that's exactly what you see here. So your photons come in, and suddenly the forward times moves, forward in phi is a time-like direction. So you want to introduce classical phenomenological perturbations to space-time, to make progress, but you want to introduce them in a way that do not introduce pathologies and do not mess the signature of your metric, right?
Is it equivalent to saying the tiny mu corresponding to your perturbations need to satisfy the energy condition?
That will be, most likely that's an equivalent thing. Of course, we don't plug it in, we don't calculate it.
But there is an effective
but there will be an effective thing. So we went back and started reading papers from the 50s, and of course Reggie and Wheeler have calculated the most general form of perturbation in a space-time. You can do it for Schwarzschild or Kerr, we did it for Schwarzschild space-time. You can write the most general form of perturbations, you can decompose them to even a node of them, and then you can put limits on the amplitudes of the perturbations in the various metric elements such that the signature of the metric doesn't change. That took some effort to understand, pure mathematical relativity, but now we have it under control, so we can do it. So what did we find? I mean, you can pretty much guess what happens. This is the Schwarzschild case. The photon orbit is somewhere there. That's why everything that goes inside the photon orbit goes into the black hole. I'm going to keep on coding blue the null geodesics that would have fallen in had it been Schwarzschild. So if you see blue geodesics that come out, it means that you can actually, what would have been in the shadow won't be. If you see red geodesics go in, it means things that were not in the shadow will now go in. And this is just a 0-0 mode, just a breathing mode of the space-time. It's clear what happens, as the space-time oscillates a little bit. The photon orbit is a maximum of the effective potential, so it doesn't take much to add to the effective potential to your metric in order to move that maximum left and right quite a lot. So you can add a few percent perturbations and get ordered unity change in where the photon orbit is, in which geodesics go in. And You can do an L equals 2, M equals 2 mode. And of course, you see the nodes in the two opposing directions that oscillate left and right.
So what is V?
V is the time-like direction in Eddington-Fickel's time coordinates. So this is the amplitude of one of the components for one of them. So this is the time-time direction, yes.
And the time scale for the oscillation is much shorter than the light crossing time?
So it is of the order of light crossing time. I mean, everything has a characteristic scale of m, so that was the idea. Of course, if you have something that is extremely slow, then you get individual snapshots of the scintillation, of the perturbation. If you have something that is extremely fast, the photons will go through and will not care about that. So this is the characteristic scale that matters. And if you believe that everything scales as m, this is the characteristic scale.
And the motivation is the information particle.
The information is that the motivation is that if you have fluctuating horizon scale perturbations that are necessary to resolve any of the fundamental problems with black holes, this is the characteristic scale. That's what it's going to look like. Now again, we're taking a big step here. This is a funny situation where the photons have a wavelength. We treat them, photons as classical, right? They're classical particles that fall on geodesics, and they have a wavelength that is infinitely small compared to the wavelength of the quantum fluctuations. So here, the quantum fluctuations are ginormous compared to the classical tiny little photon. This is a funny thing to say. And you might ask yourself, how do they two couple? The assumption here is that just the photons follow whatever the geodesics of the appropriate spacetime at this point.
How comparable is this frequency to the quasi-normal mode frequency?
Comparable. I mean, they're all 2s, pi's, and 4s, and whatever. Yes.
So if you look at the fluctuations that are a short-term radius away from the horizon, or
we have a perturbation e to the minus r squared with a characteristic scale of 1 n. Okay. So our perturbations die with n.
Okay, and so if you tune this to the scale to be smaller and smaller so that you approach more and more the horizon, so if you are Planck length away from the horizon, then all this disappears?
You're dead, yes. Everything has to be about n. Absolutely. This is the whole idea.
Yeah.
And of course, you can have with the other question is what happens if you have a complex spectrum of perturbation? You don't expect a single mode, you expect a wide range of L and M modes and a wide range of frequencies around the characteristic scale. And this is just to show that, of course, it becomes complicated. But these are all just to get some intuition for the next set of plots. What matters is what it would look like when we take the picture. And these are the kind of semi-analytic models, not the numerical ZRMH, the simulations, because I wouldn't know how to write ZRMH.
I was wondering how you're going to do the simulation.
We barely could do the photons, let alone ZRMH.
Is this image time dependent?
So exactly, the image will be time dependent.
So then if you measure it at different times, you can see maybe that's the easiest signature. You will see things shifting around.
2 slides. So, so this is what the Schwarzschild black hole would look like, and this is meant to be a very analytic plasma model to get the basic structure right, because we have no idea how to do that calculation for time-dependent spacetimes. This is what the L equals 0, M equals 0 mode would look like. And again, you have a few percent perturbation in the space-time at the location of the photon orbit, but that is a location of the maximum of the potential, so that moves the photon orbit left and right quite a lot, because it's a maximum that you can move a lot. And of course, that's what determines the location of the shadow. When the shadow is very small, you say nice photon ring. So this is what, in principle, a single mode would look like. And if you want the spectrum of perturbations, it gets more fun.
What is the source of light?
This is the plasma that is all around the black hole. So we put a semi-analytic plasma physics model and we calculate the wave transfer through that. So because the plasma ends at 6m, effectively the ISCO, and there the perturbations are really, really small, we don't put back reaction of the metric on the plasma. In principle, you need to put everything together. So
in addition to how it would look, wouldn't it show up dramatically in the light curve?
Yes. So at that level, the light curve does not change as much, and there is significant variability due to the accretion flow, as I showed, things move left and right. Perturbations like that in the shadow are probably already excluded by the existing data, that after a few years, a couple of stations with AHD showed consistent observed sizes and everything. But this is just to show that.
But the average over time is much longer than n.
Well, so what is the characteristic timescale? That's the question. Well, it depends on what source you're looking at. Sachdev stars, the center of the Milky Way, M87, they have a factor of 1,000 different masses, and if you calculate what the characteristic timescale is to pi over that omega thermal, it is an hour for Sachdev star, and it's 60 days for M87. So if we do have fluctuations like that in the black hole in the center of the Milky Way, since we have to wait for several hours for the Earth to rotate to sample the interferometric data, it will be in the ferrometric visibilities, but we won't be able to take snapshot images. We'll have to be able to dig that information out of the time variability within the ferrometric visibilities. However, with M87, every snapshot will take 5 or 6 hours worth of integration. You take a picture, you see a shadow, you take a picture, you see a different shadow, size, shape, whatever you want. And if it turns out to be different, let alone achromatic, the HT will observe in 2 different frequencies, wavelengths, 1.3 millimeters and 0.86. If you get the exact same 2 black hole shadows in 2 different wavelengths, but different from day to day, from year to year, then you get something that you can do.
There should be 1 day, not 60 days, because it's almost 10 to the 10 solar masses, and 1 kilometer is m for 1 solar mass.
Correct.
So it's 10 to the 15 centimeters divided by c. That's a day. That's less than a day.
And then there's a factor of 2 pi, and then in any case we can figure it out. I'm sure
the light crossing time is just 1 day.
The light crossing time is smaller, but it scales as the light crossing time, but has different factors in front. So that means 3.
Yeah, but if it's 1,000 times bigger, why is
not.
the time scale?
The time scale is 1,000 times slower, longer.
Oh,
that's 50 days, and that's a day, in hours, right? 6 days an hour. And the good thing with that, of course, is that for our observer friends, it gives them reason to go and observe the day after, but a year after, and then a year after, and then a year after. But in any case, this is something that you need to be able to dig out from the interferometric observables as a function of time and decompose from the variability in the accretion flow if something like that happens. And again, a lot of ifs involved, but this would be the observational signature. Look at M87 today, look at M87 a month later, a year later, and see if you have any evidence for the geometric effect, which is the black hole shadow, the gravitational effect changes as a function of time. And that's what I wanted to say. Thank you.
Questions?
So Dimitrios, is this stuff coming across the shadow in the middle? Is that also from the back, or is this some emission from the accretion in the foreground?
So it's half and half. So some of this is from the front, and that is from the back. So photons come in, go out, and go in the back there, because we have something that is oscillating. Something that I didn't show is that there are particular photon orientations that you can put, that you can actually send a photon from the outside and you can trap it in. Because that's the space-time moves around, then you'll actually trap it in some funny different quasi-spherical orbit. These are volume 0 orientations, so I do not know if they're going to have any effect, but this is something that is actually interesting. The idea of what is the null geodesic dynamics and all the chaotic properties in time-dependent space-times is something that nobody has really done anything about, and becomes relevant for electromagnetic counterparts of LIGO events. If you have 2 neutrons that you form a black hole with a highly time-variable space-time, or 2 black holes merging, and you have matter around, what are the signatures in the time-dependent null geodesics? And there's a lot of good mathematical physics to be done with that.
So, the latest equation of state for neutron stars implies that they are, as we heard from Priyal, quite compact, not much larger than the Schwarzschild radius, the corresponding mass. Right? You take 2 solar masses, and so would these fluctuations appear in the context of neutron stars or not?
This is something to somebody else to ask, but I think this is the whole issue of the information paradox is related to the presence of the horizon. Right. Everything is completely causal in the neutron stars, so I don't see why you would have.
The question is what triggers these fluctuations? In other words, would you get them in a neutron star case?
So in the talk that we had before is a tunnel, 2 weeks ago, is during the formation of the black hole itself, just before the formation of the horizon, you tunnel into in the collapse, you tunnel into a situation where you have all those rapidly fluctuating structures, whatever those are.
So until you cross the horizon, you don't get them the same.
I don't know. Something that is might be a theorem, but nobody has ever proved it, is that non-neutron star, stable neutron star configuration exists inside its photon orbit. Now, all the limits of neutron star masses and radii, Kozalka and this and that, do not require that. But nobody has ever come up with a neutron star equation of state that makes the neutron star inside its photon orbit to be able to see like lensing, like strong field lensing effects and shadows and things like that for the neutron star. There must be an underlying vision, but it's not obvious to me.
So along those lines, I was encouraging Andrea to calculate the tunneling in the presence of an effective potential for dense matter. So if we're looking at the black hole formation and you have this effective potential of many fermions, and you bring one thing in, you bring your brain in, or you bring your next fermion in, or what would that tunneling look like? Yeah, it's a very hard problem.
Questions? I was curious about, have you tried using a light curve for this, following up on Mark's point?
For the flux, yes, and the flux does not change that much. The thing with lensing is that it practically preserves, you know, in the weak regime it reserves surface brightness. Here it doesn't, because we lose some photons that should have come to you, but the oscillation is not that much. This will make enormous difference, of course, is in the amplitudes and phases, polar amplitudes and phases. And we have so far so few triangles and baselines that you can actually rotate everything and hide most of the effect, but I haven't spent too much time talking about any particular, I mean, this is an acute example of a big variation. I don't expect it to look something like that, but when we have the actual data, it's mostly a qualitative effect. The black hole shadow should be fixed every time you observe. If it isn't, the only thing that you have to say is that the space-time is changing with time.
I think instruments screwed up.
Sure. Sure, I think Seb is about to come in.
I'm sorry, I did have a question. For M87, and for matter orbiting around, does this have an effect on matter? And we're changing the jet launch characteristics close to the event horizon, and can we see that in a jetted source in relativistic outflow?
This is another thing. The minute the space-times become significantly different than here, then you actually, your orbits become almost stable in the radial direction, so you actually lose the risk goes all the way, all the way to the horizon. But the orbits start to become unstable in the vertical direction, perturbations in the vertical direction. So again, this is pure mathematical properties of the orbit. So if you have plasma coming in and your space-time is significantly different than here, has significant quadrupole moment, then everything is going to start, it's going to get launched in the vertical direction along the spin axis. Is that
So you're saying that this causes jets?
Not this, even if the space-time is time independent, you have the same issue. Is this the physically relevant? And I don't know. I mean, let's get the data and see how the thing looks like, and we'll think about afterwards. But this whole idea of stable orbits up to some radius, everything going in, and nothing unstable in the vertical direction is very particular to the no-hair theorem on the Kerr space-time.
Okay, well, let's thank both our speakers again. Yeah.
No, I will